Hi there, guys. Okay, today we're going to be looking at the Earth's energy budget. So, as you all know, we get our Earth's energy from the Sun. Here's the Sun, and here's planet Earth. I know, I mean, actually, of course, the Sun's much bigger than that. But what I want to demonstrate to you here is the amount of energy which the Earth receives. Now, if we could draw a little window in front of planet Earth, something like that, and let's say that window was 1 meter by 1 meter, so it's 1 square meter. And if we were to put this window right at the top of the atmosphere, the amount of energy going through this window would be 1,367 watts. 1,367 watts. That's right, the units. So it must be watts per meter squared. This number 1367 is actually known as the solar constant. I know we call it a solar constant, but it's not actually absolutely constant. It does actually vary a little bit, but let's call it S, which is the solar constant. So that is the amount of energy traveling through this window at the top of the Earth's atmosphere. Let me just draw here's the Sun's energy traveling through this window here. So, scientists know that this figure is true because they can look at the color of the Sun, and from the color of the Sun, they can see how much energy is being given out by the color of the Sun, because the frequency of the light determines the amount of energy which is given out. Therefore, if they know the temperature of the Sun, they know how far we are away from the Sun, and therefore it's not so difficult to calculate what the solar constant is. But secondly, of course, we have satellites in orbit around planet Earth, and they can roughly measure what the solar constant is, 1367. So let's just clear some of this away. Okay, let's draw planet Earth again. Let's show the Sun shining on planet Earth. And let's remind us of the solar constant, which is 1367 watts per meter squared. Now, because the Sun is very hot, it sends its energy to planet Earth as shortwave radiation. This includes visible light and ultraviolet light as well. This energy then heats planet Earth up, and because planet Earth is being heated, it starts to get hot, and then planet Earth will actually start to emit radiation out in all directions like this. Now, the energy being emitted out from planet Earth, because planet Earth got hot, yes, that is emitted as long-wave radiation. Now, if planet Earth didn't emit long-wave radiation, then no energy would be leaving the Earth. But that would be a strange situation, because then the Earth would just get hotter and hotter. So actually, the amount of energy entering planet Earth is the same amount of energy as coming out of planet Earth, and that keeps planet Earth at the same temperature. And it's this balance between the energy entering planet Earth and the energy leaving planet Earth, which is what the Earth's energy budget is all about. Okay, so we know the amount of energy which is entering planet Earth at this point here. So this would be as if the sun is directly above you. But in this diagram, what about on the other side of the world? Well, obviously no energy is entering planet Earth. Yeah? What about at the North Pole or at the South Pole? Yeah? What's the amount of energy which is entering the Earth? Yes. What about, at these latitudes here, this latitude here, or this latitude here? What's the energy entering the planet Earth there? Yeah? So we know it at this point here. It's 1367 watts per square meter, but of course, that's the maximum amount because the sun is directly above planet Earth. On other places around planet Earth, the amount of energy entering planet Earth from the sun is obviously less. So we need to calculate an amount which is like an average for all the surface of the Earth. So to find the average energy shining on planet Earth, we need to take the total energy shining on planet Earth and divide it by the area of planet Earth. The easiest way to calculate the total energy shining on planet Earth would be if we imagined, for example, a screen, and we put the screen behind planet Earth, something like this. There's the screen, and the sun is shining on the screen. Well, the planet Earth would leave a shadow on the screen. So the shadow would look something like that. So if you were to imagine the sunlight now falling on the circle, that would be the amount of energy which is shining on planet Earth. So then we'd have the total energy, and we'd need to divide it by the actual surface of the sphere, which I'm sure you know how to do in mathematics, and that would then give us the average energy shining on planet Earth. Now, as it happens, as it sort of works out, there's an even easier way to work it out, and that is just to take the solar constant 1, 3, 6, 7 and divide it by 4. And the reason is because if you were to take the surface area of the circle here, you could fit 4 of these surface areas onto the surface area of the sphere of planet Earth. So that's how we actually get to that calculation. So, and that comes to 342, and that's the average energy intake per square meter, of course. So per meter squared. So we said that 1, 3, 6, 7 watts per square meter was the total amount of energy received by planet Earth as if the sun was directly above us, but then we need to divide that by 4 to get the amount of energy which is taken in by planet Earth as an average for all over planet Earth, and that figure was 342. meters per meter squared. So remember this figure, and I'm going to clear away everything. Okay, 342 watts per meter 3. Ah, sorry, that should be per meter 2, shouldn't it? Let's change it to a 2. So let's draw planet Earth again. And we know on average that the amount of energy shining on planet Earth on average for the whole world here is 342 watts. Now, not all that is absorbed by planet Earth. A lot of it is reflected away. So let's imagine a ray of light striking planet Earth. Some of it is absorbed by planet Earth, but some of it is reflected away. In fact, 30% is reflected away. But we are interested in the amount which is entering the Earth. Yes, so still some is absorbed by the Earth, and we need to calculate what that amount is. And of course that's a very easy calculation. We take the 342 and we multiply it by the 100% minus the 30, which gives us 239, and that's going to be watts per meter squared. So this figure here, 239 watts per meter squared, is the amount of energy which is absorbed by planet Earth, because 30% of it gets reflected away. Just as a matter of interest, this energy which actually gets reflected away here, this 30%, we actually call that the albedo. And the albedo for planet Earth is about 30%. So we've had a look at the amount of energy coming into planet Earth. Next lesson we're going to actually have a look at the amount of energy leaving or being radiated by planet Earth. Okay, see you next lesson.